Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hello and welcome to episode 171 of the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. I am Tim Robertson, the host of the podcast, and also the coordinator of the training program in the ALPO. Thanks for downloading. Thanks for listening. The ALPO collects and analyzes observations of various solar system bodies and associated phenomena, and publishes detailed reports concerning these bodies in its quarterly publication, the Journal of the Association of Lunar and Planetary Observers, known as the Strolling Astronomer. This podcast depends upon donations from you, our listeners, to keep it going. If you enjoy what you hear on the podcast, you can subscribe by donating as little as $1 a month. If you're even more generous, for $5, you receive early access to the podcast before it goes public. For a monthly donation of $10, you receive a copy of the Novice Observer's Handbook, and for $35 a month, you receive producer credits on the podcast. You can find out more by going to www.patreon, that's patreon.com/Observer's Notebook. And if you'd like to join the ALPO, membership begins at $22 a year. You'll find out more at www.alpo-astronomy.org. And you can also find us on Facebook. Just search for ALPO Astronomy, and this podcast also has a Facebook page as well. Just search for Observer's Notebook. And if you enjoy what you hear in the podcast, please subscribe. That way you'll never miss any episodes. And now, episode 171, and we're talking to the most recent recipient of the Walter H Haas Observers Award, Trevor Barry. Hope you enjoy. All right, I'd like to welcome everybody back to this edition of the Observer's Notebook podcast. And today we have a very special guest, Trevor Barry. How you doing, Trevor?
I'm very good, Tim. Great. How are you?
I'm marvelous, and I really want to thank you for coming on the podcast, too.
Oh, it's my pleasure.
Now, before we get into talking about what you're doing in astronomy, just can you give everybody a little bit of background about yourself?
Well, I tell my wife and young son, he's unfortunate to have old parents, that I'm a super fit elite athlete approaching 72. I live in Broken Hill, the remote outback of Australia, 2,000 kilometres west of Sydney.
Oh.
You can't go any further west of Sydney and still be in New South Wales. A native of Broken Hill. And I worked in the Broken Hill mines. We have mines that have been in production over 100 years now, for 34 years. I started in the mines in 1969 as an apprentice fitter and machinist. And while 10 years in, did the electrical trade course from the ground up. So I was a dual tradesman. And after 34 years, I finished up in March 2002. Had sort of got into astronomy very casually during my working time on the mine.
Okay.
But I sort of wondered, that intrigued me, why the stuff I looked at through my scope looked the way it did. So I pulled on a postgraduate degree in astronomy. That was a bit of a thrill because, I left school early to go and work on the mines. So I had no tertiary background at all. Did TAFE. My trade course was done at the local TAFE. So a bit apprehensive, but I knew some professionals who'd actually been out and visited my observatory, and they were very supportive of getting into it, and I did all right. So, yeah, that's me.
Okay, so you got into astronomy a little later in life, though, didn't you?
Well, Tim, look, most people don't look up, and sadly, I was one of those.
Yeah.
And so in my department on the mine, the apprentices that work on our mine, it's a very big concern. It was a very big concern, and the apprentices got very good training because they would rotate through all the different departments on the mine that did different types of mechanical or electrical engineering, like underground, surface, whatever. Mm-hmm. We even had our own power station, our own engineering design office. They would spend time even there. Well, one of the apprentices that came through my department, him and his dad had built a telescope. Like they'd even ground the primary mirror.
Oh.
It was an 8-inch Newtonian reflector, and they built a German equatorial mount out of pipe fittings.
Oh, my.
He asked me to go and have a look at it. Well, I had no interest in why would I want to look through a telescope? But he was persistent. And, our town's only very small.
Mm-hmm.
It was the middle of winter, and my wife's mum lived the other side of Broken Hill. So that's a 10-minute drive.
Okay.
So I dropped her out at her mum's place. It got dark early, middle of winter. So I went to have a look at this lad's scope, and it was on the back lawn behind his house. And, from an engineering viewpoint, it was actually quite impressive, and I sort of wandered around and checked it out. And then he just pointed out this nondescript point of light. This is what we're going to look at. And I thought, oh, well, this won't take long. So I looked, and there was Saturn.
Uh-oh.
Ring system, Cassini division, I don't know, 4 or 5 moons, spread out either side. I thought, this can't be right. How can this possibly be? And, one thing led to another, and all these little patches of fuzz that are there every night, but no one sees them, and they became globular star clusters, open or galactic star clusters, emission nebulae, like it's amazing stuff. I picked the wife up 2:00 the next morning. I was in bother. So it's something I had to get into. So that started me. So I built my first telescope, and, then this aperture synthesis, so how to build a bigger one. And this went on, and we used to have a back lawn. And I got into bother with the missus. I got a post hole digger and sunk 3 holes in her back lawn, and 3 2-litre plastic ice cream containers in there filled with concrete. And I built a German equatorial mount on a pier, and it had 3 legs, and I slotted lawnmower wheels into 2 of the legs so I could lift the 3rd one and sort of wheel it from underneath our back veranda. The telescope used to live on a bed in the house with a sheet over it.
Okay.
And one day, fateful day, had all the counterweights on it, not the telescope, and I was wheeling it out from under the back veranda. And I lifted the leg that I'm, wheelbarrowing along with too high. Newtonian physics took over.
Oh, no.
Launched me over the top into my gorgeous and adorable wife's rose garden.
Oh, no.
And let me tell you, the roses weren't damaged, but I was. So this sort of led to an observatory.
Of course.
It was single-story observatory, rotating dome. They're designed and built our local technical college on Wednesday nights. They had a night class, and I could go along and just use their equipment, their lathes, millers, whatever.
Wow.
And so I built various equatorial mounts and built my own drives and used synchronous motors to turn the drives, and and then I had to go bigger again, and the telescope kept getting bigger, and I wanted a big one. And I sort of looked around, and I saw Meade had a 16-inch Dobsonian telescope.
Oh, my.
I didn't want a Dobsonian telescope.
No.
So I bought that to side in it with a 16-inch primary mirror, and I built a massive German equatorial mount that's very heavy. Like the cardboard tubes, I don't know if you've run into them, they're very thick, and there's a lot of weight just in the tube, and of course, then I wanted to go bigger again. So I went 2-story. I went from a single-story observatory to a 2-story observatory. Got heaps of stuff downstairs, all my work, a lot of work on display, and I designed and built my ultimate telescope, which is for what I eventually got into, which is planetary imaging. And the tube is aluminium because aluminium follows the ambient temperature, so steel tube will go below ambient and dew, and then you'll get tube currents. And, I image at 2000 power. So the air that's in contact, the boundary layer of air across the primary mirror has to be at ambient. And so the mirror's got to be at ambient. Right. So I built a Peltier cooler, and I run that for 2 hours before I image. And so I drive the temperature of the Pyrex down, so I get a window of about 2 hours where it's near enough to ambient that I don't generate currents in that boundary layer of air. Okay. I don't get tube currents because the tube is aluminium. It's a Newtonian reflector, but it's different. Every Newtonian reflector I'd previously seen had a push-pull cell to change the angulation of the secondary mirror. So to do that means tightening or loosening one of 3 screws, or maybe 2 of the 3 screws, to change the angulation of the secondary to collimate the secondary. But that's no good. It's all right just using eyepieces, but at 2000 power, that's a problem because you're instigating a turning moment. So you can flex 1, 2, or maybe 3, or if you've got a 4-vein spider, those veins, you can put a flexing moment into that, which at some point through the night might release, so you lose your collimation. So my system has a very large, heavy aluminium ring outside the tube that sits on Teflon. And I've got a 3-vein spider. They're 3 stainless steel machine rulers, like engineering rulers, and they pass through slits. My push-pull adjustment shifts the entire vein longitudinally, so there's no turning moment at all to release at some. I'm very pedantic. I can't help it at 2 a.m. There's nothing perfect in this life, but it's a very good telescope. Wow. Newport Glass in California did the primary for me, and I had it rough cast, so it's 16, over 16 inches, 605 or 606 mil diameter. Wow. And it's rough cast f4.5, and we have one master mirror maker that I know of in Australia. He lives in Sydney, and I left the mirror with him, and he spent 6 months on it, finishing it. Again, there's nothing perfect in this life. However, Jesus, a good curve.
This is the Dobsonian mirror that you bought?
No. This is another mirror. Okay. I've moved on from that. Okay. This is my ultimate telescope. Okay. So secondary from Antares Optics, also in California, and I specified. So that's the difference between the highest peak and the lowest trough is 1/30th of one wavelength of light. That's military spec for that surface. So, and then I live in a really fortunate position. Like we're far inland, it's very flat. So we have laminar flow of the weather systems as they traverse our continent, west to east. And there's no big snotty mountains or even large hills to delaminate that flow. And then the high pressure systems that across Australia very often pass directly over Broken Hill, which pushes the jet north and south giving me really stable air over the top.
My goodness.
And then also being so far inland, generally, we have very low relative humidity, so very low levels of water vapor in the atmosphere, which is also a big help. And, so that's sort of me.
Wow. So you've built all of your telescopes pretty much then, right? From the ground up.
Designed and built the observatory, designed and built the mount that the telescope swings on, designed and built the telescope. I used a friend of mine put me onto a ray trace program called Newt. It's a very old program. And I used that to design the telescope. I've never had an eyepiece in it. It's designed to be a lens for my imaging train.
Okay.
The position is fully baffled. The position of the baffles is determined by the software program, based on the wavelength of light, so I don't get scatter. So as I said, I'm a very pedantic person.
Very good. Now, let's go back to your first one, the first telescope you built. What was that?
That was a 10-inch Newtonian reflector. And for that one, I got onto a company that built like drainage pipe, stormwater pipe, plastic, PVC. And so I got a length, 12-inch diameter. So what about 6 foot long length of PVC stormwater pipe? And put my primary in that. And, this was way before I ever got into imaging. This was just, looking
visual
through the sky. Just introducing myself got a decent atlas, Sky Atlas 2000. And just work my way star hopping. Actually, that's the way to go.
Yes.
But people that have computer-driven scopes, they miss out on so much.
Yep.
By star hopping from the current object that you're looking at. It's just amazing the stuff that you come across while star hopping to the next thing that you thought you wanted to look at.
That's a good point. Thing you thought you wanted to look at until you find something along the way. That's a good point. Yeah. Do you think working in the mines helped your night vision at all?
Well, working in the mines, if I hadn't worked in the mines, I couldn't have done what I've done with astronomy. Like we're very remote, and so I do mechanical maintenance, later electrical maintenance, and often equipment would break down, and it would have to be fixed, and we wouldn't necessarily have the correct part, and so you'd have to think outside the square to come up with a solution to get that equipment online and running. So I think it taught me to be very resourceful, and and that sort of helps. Like among other things, now I play lawn bowls, and I'm the greenkeeper at our local bowling club. My adorable wife is the secretary treasurer, and I was bored out of my brain doing really mundane tasks, walking up and down behind various mowers and other implements. I have some of my best ideas of how to improve my capture regime, how to improve my processing regime. I've got a very well-equipped workshop, nice lathe, post-drill, grinders, what have you. So if I hadn't worked on the mine, that gave me the skill to actually build a dome, petals, like how to calculate the curve on the sides of the petals, how to generate that to come up with something that actually looks like an observatory and works. And then other things like we're in the middle of nowhere, but believe it or not, we did have a sailing club, which we were in a long, long, long time ago.
Okay.
And so I have the trapeze wire from one of my catamarans, and that opens and shuts the slot of my dome. And then I've got an old, I don't know if you're familiar with the old Ringer washing machines.
Okay.
the chug. Well, I've got the motor of an old Ringer washing machine, and that rotates by donut. And when I fire it up, it just sounds like it too. You got to be there. Like, I love it.
Oh, that's wild. That's absolutely wild. So you're pretty resourceful.
Well, you have to be.
Yeah.
You just, if you've got to come up with solutions, and if there's no such thing, there's nothing that can't be done. You just have to sit down and think about it.
Right.
There's always a way to overcome whatever problem you might come up with, and God, once when I'd done my degree and I've always been interested in Saturn after that being the first thing that I saw through a scope, and I found my first electrical storm on Saturn, 2005, and I knew a few professionals then here in Australia, and I contacted them, and they pointed me to the Cassini imaging team. I found the Cyclops website. There was a little doodad there for public comment. But I didn't want public comment. I thought, if they don't know that this storm, I'd never seen anything like it before, was there, then they needed to know. I kept pestering people and ended up getting on to Dan Green at Harvard.
Okay.
But when I was doing my degree, I did a variable star project. And that's where I became acquainted with Dan Green, with the CBAT bulletins, some of which are about variable stars. And I contacted Dan, and there was heaps of toing and froing. Was I a dual? Did I have a clue as to what I was on about? Well, he took it upon himself to contact Georg Fischer, then at the University of Iowa, who was on the Cassini RPWS team, so radio and plasma wave science. So on the Cassini spacecraft, there are 3 whip antennae. Now, I got to go to JPL. That's another story. But anyway, and they've got a 1/3 scale model, and there are the 3 whip antennae. So his data, if you have a radio turned on in your house and there's an electrical storm near you, whenever there's a burst of lightning, you hear static. But that's all the data Georg Fischer is getting with his RPWS instrument. So
he doesn't know where it's coming from. He knows.
No, he doesn't even know what hemisphere it's coming from. So knowing the velocity of the spacecraft and the rotation rate of the planet, he could make a guesstimate. So when the Cassini spacecraft came over the horizon relative to where there was a SEDS, he called it SEDS, Saturn electrostatic discharge, outburst, it would stop when the spacecraft went over the other horizon. And so he could make a guesstimate for the midpoint, so an approximate longitude, no clue what hemisphere this was in. So this is happening deep within the atmosphere. So we've got 3 cloud layers at Saturn, pretty much all the same as Jupiter. Upper cloud layer, ammonia, ice particles, intermediate cloud layer, ammonia, hydrosulfide, ice particles, a lower cloud layer, water ice crystals. On Saturn, that's to a depth of about 200 kilometers. So from time to time, poorly understood heat source drives material from the water ice cloud layer into rapid vertical motion. Now think about this. Ice particles, 200 K deep within the atmosphere, they're just sitting there doing nothing, potential energy. But when they start surging upwards, they're rubbing against one another. So kinetic energy, build up charge, discharge, Saturn electrostatic discharge. How cool is that? So that material will continue to punch upwards, punch through the upper cloud layer. Now, this is different stuff. It's deep within the atmosphere. So, Trev, images a white spot. How about that? Very accurately, I would measure the latitude and longitude, send that to Georg, and only then could he do his analysis on the propagation of the radio waves through the atmosphere. So the first time this happened, he got back to me and he said, look, we know this storm has started. It's been going for 3 weeks, but because of the various instrument packages on the spacecraft and their priorities, He just can't have the imaging cameras used when your package might be doing something with a mass spectrometer, you know? So he was totally reliant on ground-based data. And at that stage, Marc Delcras in France, Ralph Vandenberg in the Netherlands, Chris Go in the Philippines, and would I like to be part of the team?
That's quite the team to join.
Would I what? So from that point on, whenever his RPWS instrument detected a burst of SEDS, he would send out an email to our group with the challenge to hunt down the optical counterpart to his radio source. Well, did that for the rest of the life of the Cassini spacecraft. I supported it for over a decade. Agustin Sanchez Lavaro, it's the longest pro-am collaboration I have is with Agustin. His PVOL database, actually the servers for the PVOL database live in the basement of his university in Bilbao in Spain. And I currently have 7,800 data sets, and 75% of those are Saturn data. You know, so that's just what I do. And what can I say? That's the Great Storm. So how cool was that? So December, about the 6th, 2010, Bill contacted our group. He had received a massive frequency of RPWS discharges within the atmosphere, previously unseen levels. So clearly something was happening. So we were having earthly stormy weather over Broken Hill. And so it took me about 5 days to actually get data. And it was absolute rubbish data. The data was so poor that it was even difficult to discern the Cassini division. But even though this was crap data, there was this bright, really bright, more than a spot. Well, it was diffuse because it was rubbish data, but it was there and I could measure it. Now, previously, every electrical storm that I'd found to that point, like you really needed good seeing and good data to resolve it. That rubbish data could resolve this. Clearly, it was a totally different animal. Well, by mid-January 2011, it had dredged up so much material which hit the local jet stream at that latitude. It was about 42 degrees north. The jet would distribute that material, and by the middle of January 2011, it had totally encircled the planet. So much material had been dredged up, and it looks stunning. It didn't matter if you weren't interested in astronomy at all to see this, the structure to it. It was just phenomenal. Well, in the turbulence behind the head of that storm, an anticyclone spun up, and I'm still tracking it. It's the longest-lived anticyclone at Saturn, other than this one at the North Pole, one at the South Pole, but other than those two, which were discovered by the Voyager probes in 80, 81 when they swung by. That said, I haven't managed to image it yet, this apparition, but my last data on that is in November last year, and it's fading. It's actually drifting south, which is a problem. When you look at the zonal wind profiles of Saturn, the peaks are really high and sharp-sided down to the next trough as you go from latitude to latitude. Well, where the latitude that it formed, the jet is strong. Now, this is spinning. It's a vortex, right? So it needs energy to keep that spin. Well, over the last, probably 7 years, it's been drifting south. It's just maybe 0.2 or 0.3 of a degree a year, but it's coming down the shoulder of that wind profile. It's experiencing not the wind strength that it was, and it's fading. So each year I get the Hubble data. Amy Simon, she works also with Augustin's team. He tells me that I'm a valued member of his team and that my Saturn work is fundamental to his research, and he's an old fart like me. I think I've got 18 months on him. I'm an excitable person and I can't help it. And he's the settling influence. Whenever I think I found something new on Saturn, Augustine, calms me down. And this takes me to 2014. I found this really strange structure in the equatorial zone of Saturn. It had a bright component and a dark component, and it had shapes sort of looked a bit like a letter S. And I fired straight up to Augustine, and he said, well, Trev, settle. The winds in the equatorial zone of Saturn are amongst the strongest in the solar system, approach the speed of sound. So although structure can form there, it's highly unlikely to be long-lived because it will be torn apart. So that's all right. So 2015, when Saturn swung out from solar conjunction, I found it again.
Oh.
And so I tracked it. So I tracked it for four weeks, calculated the drift rate of the feature, produced an ephemeris that predicted its position over the next couple of months. Well, Augustine, his university, has access to ALPO Observatory in the Pyrenees. I think it's a 2-metre scope. And so off went one of Augustine's teams. Augustine is tenured professor of physics, so job for life, head of applied physics and head of the planetary science group at his university in Bilbao. Okay. So, they've found it up close and personal, bigger telescope. So immediately Augustine penned a proposal to NASA Goddard, who operate Hubble, and they gave us 3 orbits of the Hubble Space Telescope, and that led to a paper we published in Nature. I love that. So I'm a co-author, and all the authors are professors or PhDs, and I'm not. I'm Trev, the ex-mine worker from Broken Hill, and but I got this lovely email from the editors of Nature, and it's addressed, Dear Dr. Barry. I love that. and then also, so they have the
You didn't correct them, did you?
No, obviously not. I love that. I also got one from Icarus and geophysical research letters. So, wow. I'm a graduate certificate of science in astronomy, so postgraduate, but that's it. So definitely not a PhD. So yeah, and then they have the affiliations of the authors. So there's the creme de la creme of universities that are into planetary science. Augustine's University, Caltech, University of California, Berkeley. I have Broken Hill Observatory. I love seeing my little Broken Hill Observatory listed as, 5 times now in Nature, 6 times in Icarus, 6 times in geophysical research letters. So, so gives me a bit of a buzz.
Yeah, you are a prime example of when I talk to groups about the Association of Lunar and Planetary Observers. A lot of it are people that have telescopes, but they don't do anything with them other than casual looking through them. And I always ask, would you like to do science through your telescope? And they're like, oh, yeah. Oh, how? And I talk about the different programs within the ALPO that you can do Saturn research that's used by professionals. You are a prime example of what can be done by an amateur, because you consider yourself an amateur still. And that's pretty wild.
Well, regarding that, the hexagon, there's a perfect 6-sided hexagon at the North Pole of Saturn, surrounds the North Pole of Saturn, and it's modeled as a Rossby wave, so a jet stream that lifts a vertical wave, and there's 6 of them, and they're straight-sided. An amazing thing. And that was seen by the Voyager probes in 8081, and for us on Earth with telescopes, we never really got a look at that until the end of 2009. The rings were edge on, and following that, the North Pole started to tilt, the relative tilt. I mean, it's inclined at 26 degrees to the plane of the solar system. but relative to our position, the angle changes depending on the position of its orbit relative to us. So the rings started to dip and the North Pole started to tilt towards us. But initially, the first few years, so 2010, 11, and 12, there was very little contrast or color difference between the hexagon and then there's a ring of material that surrounds the hexagon. And so it was very difficult to define the vertices of the hexagon. However, when Saturn swung out from solar conjunction early 2013, there was significant difference in contrast and color between the hexagon and that surrounding area. So I started a project to very accurately measure from Earth the rotation rate of the hexagon. This is a big deal.
Yeah.
So we have 3 rotation rates at Saturn: L1, System 1, System 2, System 3. So System 1 is the rotation rate, the cloud tops at the EZ, the equator. System 2, the cloud tops across the rest of the planet. And System 3 is the internal or magnetic rotation rate of the planet. Now, that was Voyager's had metal block. I'll get to that. They measured it with what do we call that? Big long boom. So the magnetic field of the spacecraft is not seen, and they measure the magnetic field of the. I can't think of the name of the. I'm old. You'll have to forgive me. Anyway, so that came up with a figure, and it's sort of 10 hours 39 minutes 22.400004 seconds. Now, there's broad agreement in professional circles that that's wrong. That the internal rotation rate is actually slower than that. Now, it's also interesting that the hexagon doesn't rotate in System 3. It rotates much slower. So isn't that interesting? So it's also broadly accepted that the processes that form the hexagon are deeply rooted in the atmosphere. And so I sort of said to my professor, I'm only an amateur, so don't listen to me. But anyway, I came out with this idea and I said, well, look, if the processes that form the hexagon are deeply rooted in the atmosphere, could the rotation rate of the hexagon actually be more of a reflection of the internal rotation rate of the planet? So anyway, 3,115 Earth days later, I produced a result. I measured, so that hexagon, the planet's rotating anti-clockwise. Mm-hmm. The hexagon's drifting clockwise relative to the anti-clockwise rotation of the planet. It's rotating slower. So I set about very accurately measuring that difference, So I made many animations. I'd animate the data. But what I did when I created polar maps in Winjupos, but I always specified the same L3 longitude at the left margin of the map. By doing that, if I made maps over however many years, it wouldn't matter. If the hexagon was rotating at the recognized internal rotation rate, the L3 rotation rate, the vertices would never move. They would always be in the same orientation. Well, over 3,115 Earth days, I measured a 30-degree drift, clockwise drift. So I had to rotate the hexagon 3,115 Earth days after the first polar map. I had to rotate that 30 degrees anti-clockwise so that the vertices lined up perfectly when blinked. Do a blink animation, blink rapidly, one hexagon was superimposed over the other. So I started out doing this on a whiteboard, and then it got very messy. So I came up with a spreadsheet and I embedded the pertinent calculations within particular cells of the spreadsheet. And when I'd finished, I sent the spreadsheet to Augustine, and I sent it to Julius at ALPO.
Mm-hmm.
And we just published a paper that might have been in Geophysical Research Letters, and it was on a two vortices cyclone-anticyclone combination up near the hexagon, funnily enough. And in the abstract, it's the closest Augustine has ever come to coming up with a relationship between the rotation rate of the hexagon and the internal rotation rate. And he went as far as saying that the rotation rate of the hexagon might well have a connection with the internal rotation rate, but not saying what the rotation rate was. Anyway, Augustine, Julius, he was impressed also with the spreadsheet, and he asked me if I'd actually produce a paper for possible for publication in your ALPO journal. And so I do nothing in half measures, so I approached it as I would one of my university papers, full in-text referencing and full reference list to follow. And I sent it to Augustine because I very much value Augustine's opinion. And I didn't want to make a fool of myself. And, so Augustine looked at it and he said, no, look, he thought it was a very good paper. And so I submitted it, and it was published last year. I think it was about June in the ALPO journal, if anyone's interested. And it's on Trev from Broken Hill's take on the differential rotation of the hexagon relative to the accepted internal rotation rate of the planet. Yeah.
Wow.
So you can do science, So what I'm saying to other people, we have other people there, other amateurs, that, think about what you do, and it is possible. I'm really passionate about this because I only saw the hexagon was only visible to me and other mortals on Earth really from early 2013, and now it's not, because now we're heading back towards the rings being edge on again, and now the South Pole is tilted away from us to the point where cannot define the vertices of the hexagon. And so the 2017 was the North Summer Solstice. 2017, yeah. So 30 years from that, it's going to be the next North Summer Solstice. Well, 30 years from there, will I still have my marbles? Will I still be on the planet? I may never see the hexagon again in my life.
Oh, my.
So I've been very, very passionate about doing something from, an amateur's perspective to contribute to that, And then I know the professional body here in Australia last year, our peak professional body is the Astronomical Society of Australia. And every 2 years, they award the Berenice and Arthur Page Medal. And it's for work by an amateur that has advanced the field of astronomy. And they saw fit to award that to me last year. And it was very, very humbling. I mean, to get that sort of recognition. And in the citation, the president is a professor of physics at Monash University in Melbourne. And in the citation, he talked about my general work in planetary science, but in particular, the work that I'd done on the differential rotation of the hexagon at Saturn. He was taken with the technique that I'd come up with, not having a gravitometer or a spacecraft, to even attempt to do that from Earth with a meaningful result. So when I actually sent my paper to Augustine, before I sent it to Julius, he said, look, Trev, there are errors of measurement in everything. There is no perfection. So even the measurements from the Voyager data that we use for the internal rotation rate, there would be errors of measurement to consider.
Mm-hmm.
So I then went back to my spreadsheet and I calculated the difference. Now, I measured a difference of 30 degrees over that time period. So I then calculated the difference, an error by me in my estimation of the rotation of 2 degrees, not 30. So 32, 28 to 32. And that error, so my measurement is to within 6 decimal points of 1 second of the rotation rate of the hexagon, and it's plus or minus, I can't quote it off the top of my head, but it's 0.03 something, and I took that out to 6 decimal places too. So
for ground-based observing to be that accurate, that's phenomenal. That's just you don't see that. That's amazing that you could do that. Wow.
Well, there you go. It's just something people can do. You can do that.
Okay, with perfect seeing and the perfect instrument, and yeah, that's amazing. That's amazing. So you mentioned the ALPO. How did you get involved with the ALPO originally?
Oh, long time ago.
Yeah.
So lots of things, serendipitous things have happened to me in my astronomy.
Mm-hmm.
So when I found my first electrical storm and became involved with Georg Fischer and the Cassini mission, Cassini APWS team, I'd started posting on cloudy nights, and here in Australia, on Ice in Space is our equivalent. And another Australian amateur, very good, very sort of genius, actually, an IT professional, and he's helped me in that respect considerably. But I didn't know he existed, and and I came aware of him, and he said, "Look," I then put him in touch with Georg Fischer, and he also became part of our little team. He was 1,000 kilometres at that stage. He was 1,000 kilometres east of me, so that gave then 2 widely separated observing points in Australia. And he pointed me to Augustine and the PVOL database, the BAA and ALPO.
Okay.
And so from that point, all my data went to the BAA. I went to ALPO Japan for a while, but then I had problems with them. They wanted everything south up, and all the papers that are published, they don't
North
publish. It's north up. So that's just how I produce it.
Yeah.
Anyway, and the ALPO.
Japan ALPO is not affiliated with the ALPO in any way either.
No, they didn't want my data. I couldn't believe that. They've numerous times since then. A couple of years ago, they changed their stance on south up, and so I started sending them data again. I send a lot of data. I just don't take happy snaps. If I image, if I have good seeing, that I don't. The sort of seeing we get out here, it's either good or it's not. If it's good, it's not suddenly bad. Mostly it's good all night. So I'll have hours of data, and I would usually go do the 9 minutes infrared and RGB. There's 18 minutes, 9 minutes infrared, and then 9 minutes methane CH4, and then I need about a 5-minute gap to before I go to my next infrared to keep the 20-minute centers between infrared data sets. Like that's where from my experience is that infrared, the really fine detail that I'm interested in is best seen mostly in infrared. So I've got 685 nanometer IR. That's currently what I use, but previously I've used 742 nanometer IR, 607 nanometer IR, 889 nanometer methane. That's 20 nanometer pass centered on 889 nanometers. And very occasionally I do Venus, and I've got UV for that. But I forgot what you asked me. I'm sorry.
No, just when you got involved with the ALPO.
That's when I got involved with the ALPO. Yeah. So
Okay.
right. Initially, once I started my work with Cassini, got fair dinkum, became a fair dinkum observer, not just a casual observer, but struck a chord with me, was something that I wanted to contribute to. I want my life to matter. That's silly, isn't it? I suppose. But anyway,
not at all. Not at all. Wow. Just imagine if you wouldn't have looked at your friend's telescope many years ago at Saturn, because that probably affected this interest that you have directly.
Well, look, when I was doing my degree, the best way to learn a subject is to teach a subject. So we've got a local community college, and so I started an astronomy class.
Oh.
I give presentations on the work that I was currently doing with my degree. If someone asked me a question that I couldn't answer, trust me, the following week when they turned up, I'd give them the answer in triplicate. And then a private school in Sydney, Methodist Ladies College in Burwood in Sydney, they started bringing their Year 9 kids to Broken Hill. They'd stay for a couple of weeks, and somehow or other their headmaster was aware of me and asked me if I'd go and give them a general presentation on astronomy, which I would do. Take a laser and walk them through the night sky with the laser, and there'd be normally a group of maybe 40 kids, and not many people are interested in astronomy. Well, one of the electives they could do while they were in Broken Hill was astronomy. So the kids that were interested in astronomy would get bussed into my observatory. There'd probably only be 4 or 5, but I'd put a spectroscope on my telescope, which I had back then, and I'd drop it on a red giant, and I'd tell them the name of the red giant, how far away it was. I had a laminated periodic table with magnets holding that to the inside skin of the dome, so I drop the laser on it, tell them, it's not just a point of light, it's got a name. This is how far away it is. Look here. And they'd look in the telescope, not see the star, but see the light from the star drawn out into a band with the emission lines of where whatever element was there. And then they could look at my sample periodic table that I had stuck to the dome. It was real science, and I got such a buzz out of that. Yeah. Teaching kids.
That is a lot of fun. That's pretty cool.
It is, yeah. So, yeah, that's the thing. I used to, with my astronomy group, I went out of my way for many years. I used to have a visitor's book in my observatory. I've got so far beyond the ability to do that my current telescope, there's so many cables hanging off of it. There's the cable, it's got a JMI cable remote focuser. So there's that comes off it, a double-decker computer hutch, computer in the top deck. I pulled a 8x50 finderscope to pieces, machined adapters to take a CCD camera, which gives me a low-power, wide-field view of the night sky. That's aligned with the optics of the telescope.
Okay.
My main imaging system now, like Exactal electronic filter wheel, loaded with all of those filters. A Grasshopper 3 camera. That's everything that I've got in there extends the focal length such that I get 2,000 power. So I wouldn't. And then there's all the cables hanging off the Peltier cooler. Everything comes back, and it's just not a telescope anymore that you can just swing around the night sky.
Right.
Like I can follow the path of the planets across the sky. That's what it does.
That's what it's built for.
That's what it's built for, and that's what it does. Yeah.
Yeah. So your current telescope, what is? I don't think you really talked about what it is.
Well, it's a 406, I think, millimeter, 16-inch primary. That's from Newport glass in California. It's the aluminium tube.
Okay, that's the one. Okay.
The totally different front end, not a typical Newtonian front end with the push-pull. Like my system for adjusting the angulation of the primary cannot untwist or whatever through the night, So, yeah.
Okay, so what are your future plans?
Continue. I've lost the hexagon. I'd love one more time to get the long-lived anticyclone vortex. A couple of nights I've had good seeing, but probably closer to opposition. So August, hopefully I'll get good seeing, and maybe I'll crack one more time. When we do lose it, because I've tracked it for so long, and all that data I have in spreadsheets with drift charts, and Augustine's team will use that, and we'll publish a paper on the longest-lived vortex seen at Saturn.
Fantastic. Any equipment upgrades you're looking at, or are you pretty much set with what you got?
Well, my good friend Anthony Wesley, I told you about, who I fell upon, he's a whiz kid, a computer whiz kid, IT professional, and he kept telling me it takes me a long time to process my data. So a night of capturing data, so that camera's capable of 8 or 16-bit data. I capture 8-bit data. Saturn, I do it 72 frames a second, so that's a lot of data. I've got to dump that onto an external drive. I was using a 2 terabyte external Seagate drive, and then I have to process off of that, and then I dump it onto an archive drive, a 5 terabyte archive drive, and it would take me maybe a week and a half to process a night's data. And my mate Anthony, he kept complaining about my steam-driven computer. All my gear is old. All my gear is old gear. But my fastest computer, my newest computer, which isn't new at all, but anyway, this is the one I'm using with you here now.
Okay.
He pointed out this thing, a StarTech SATA hard drive dock, and it's a really interesting contraption. And this has got USB 3.0, two USB 3.0 ports. And if I use a solid-state external drive, there's still a bottleneck, and it's not fast to process, and which takes hours and hours and hours to process. Well, with this SATA hard drive dock and a solid-state drive, but a bare solid-state drive. So I'm using a 2 terabyte Samsung bare solid-state drive. So there's not a cable coming off of it.
Okay.
The end is open, and the copper contacts are visible. Well, the dock has a slot in the top of it that opens, and you push the solid-state drive, the bare contacts, down into it.
Oh, my.
The electronics inside there that do magic, and like I use auto stacker, that's the longest thing, the stacking of the data. And where it was taking me better than 5 minutes to stack 1/92nd at 72 frames a second run. If it's good data, I'd stack 80% of the frames. If it's rubbish data, I'd stack 50%. I'd never stack less than 50%. But it's better than halved that time. So it's gone from 5 minutes to pretty much 2 minutes smack on. So more than halved the time that it takes to stack a 90-second run at 72 frames a second. And that's a big help to me.
Yeah.
And it's not an expensive bit of kit. I think in Aussie dollars, this dock was about $130 Australian.
Okay.
And I think the bare solid state drive to slip into it, that'd be a 2 terabyte. Because I need to cover the situations where something out of the blue happens to me and I don't get to that data before the next data run.
Mm-hmm.
Like often, if I get 3 or 4 successive nights of good seeing, other than it's impossible to talk to me, I'm in a daze, lack of sleep. I'm fine when I'm down there. I fire right up as soon as I see good data coming in. I'm a buzz, but
okay.
I haven't got to the previous night's data. There needs to be room on that drive.
Okay.
Take another lot, So yeah.
Yeah. So how often do you go out? Just whenever it's clear?
No. I spend my life looking at computer models for the jet stream.
Okay.
The GFS 200 millibar isotax, they're a very good indication. Skippy Sky, I look at Skippy Sky, not the Skippy Sky prediction for seeing, but I look at Skippy Sky prediction for the jet stream.
Okay.
More so, and the position of the high pressure systems. If we have a high pressure system over the top, I haven't had bad seeing.
Okay.
And then I use my eyes. So I'm outdoors a lot working at the bowling club, and the jets that come over from Melbourne going to Japan or from Sydney going to Perth. If there's no vapor trail at all, then look, there's just no water vapor up there. Or if there is a little vapor trail and the vapor trail isn't dispersed, because of wind shear, that also could be good.
I had never thought of that. That's
use your eyes. Look at the sky. Also, I've had heaps of TV crews come out and do stories on what I do. And almost always the cameramen always make the point as to how blue the sky is out here. We're a long way from anywhere, Tim. Like pollution, other than the occasional dust storm in the summer and the sky goes red, but I mean mostly, there's just, we don't have atmospheric pollution, and the sky is a really deep blue. It's some days more than others, and it's really noticeable. It's really noticeable, like the clarity of the sky. Yes, it's just fortunate to live here and be interested in what I am.
That's fascinating. It really is. Well, do you have anything else you'd like to share with our listeners?
Oh, well, what else? The keks. So when I did my degree at Swinburne, my final unit, my unit instructor was Professor Duncan Forbes. And actually, it was on the distance to our galactic center. He deducted 1 mark. That's the highest mark that I got at uni, Anyway, so 12 months after graduating, I found a storm and I got heaps of publicity, heaps of press internationally and here in Australia. NASA put out a media release naming Mark Del Cra, Ralph Vandenberg, Crisco, and Trev the Mine Worker. Trev the Mine Worker for their support of the Cassini mission, Anyway, The Age, which is a major metropolitan newspaper in Melbourne, where my university is, they sent a journalist and a photographer to Broken Hill, and they did a full-page story on that. And before it went to press, the journalist contacted me, said, Trev, couple of questions for a little CV, top right-hand corner, one of which, did I have any unfulfilled ambitions? And I said, Struth. Wouldn't it be great to go and observe with the keks? At the time, the largest optical telescopes on the planet. Well, Duncan contacted me and he said, Trev, my university has a supercomputer right? So that I was with astrophysics and supercomputing, and they have an astronomy section, which Duncan is part of. So the KECs are operated by Caltech.
Mm-hmm.
They give Swinburne, it's the only Australian university with a time allocation on the KECs. They give them 20 nights. And the spin-off is Caltech get to crunch data on Swinburne's supercomputer. Well, Duncan contacted me and he said he was taking 2 PhD candidates to Hawaii. They had 2 nights on KEC 2. Would I like to go? So I had to pay my way, but I went with a professional research team.
Wow.
And so we drove to the summit. We drove in four-wheel drive, diesel four-wheel drives, like the waiver I had a sign from Caltech to get access to the KECs, everything I could die from, cerebral edema, what have you. And all the information they sent, it's a matter of course, people dosed on high concentration aspirin to thin their blood to make less likely altitude headaches, what have you. And we stopped at the Onizuka Center for International Astronomy, which is halfway up the mountain. There's a barracks there. And the observatories that don't have remote access, the operators, if they're whatever, they may have a week on, week off. Well, instead of going 14,000 feet to sea level, a day, they go 14,000 feet down to 7, the Onizuka Center, that barracks, they'd stay there for the time that they were on, So we stopped there for 2 hours to acclimatise. I popped 250 milligram aspirin, and away we went, drove through the cumulus cloud layer. Absolutely amazing experience, up the top. Such a alien environment, ochre red cinder cones, grey fractured lava, and you're above the cumulus cloud layer, can't do anything quickly.
No.
So, it didn't really, I was just ablaze to be there, honestly. But they took us in and sat us down and went through all the symptoms, any of which, if we felt, we had to tell them, and they whistle up a chopper to get us down to lower altitude. And everyone with a thinking job had an oxygen bottle on a leather belt behind them, dosing tubes into their noses. Well, and the operators of KEC 2, they even slewed KEC 2 over far enough so that I could take a photo of my reflection in the largest primary mirror on Earth.
Oh, how
buzzing.
Cool.
So, but then we had our 2 nights. The KEC headquarters is at Waimea. See, that's only 3,000 feet, So that's where we observe from, the KEC remote control rooms. KEC 1, KEC 2, they're back to back. So we were in, summer wear, and we had 2 operators at the summit, and they had to eyeball one another every 40 minutes to make sure they were still alive. And our second night, Duncan took me through to KEC 1 control room and introduced me to Chuck Steidel, a Caltech astronomer, and it was his first of 2 nights. And let me say, I'm only an amateur, I know nothing, but I enjoy what I do. And every time I've met a professional, they've never looked down at me or been condescending. And like, he gave me 2 hours of his time and explained to me what he was into, which was he was using background quasar and a spectrometer to detect intermediate clouds of hydrogen. It was thought there was nothing between the clusters of galaxies, but there's these odd clouds of hydrogen out there. They're doing nothing, but if he lines one up with a high energy source, i.e. a quasar, then he can detect absorption lines, emission lines from that intermediate hydrogen, and they call them Lyman alpha clouds. And where there's a lot of them in that particular plane, they're called Lyman alpha forests. And that was interesting. So the next day, bear in mind, I've just had 2 all-nighters and I'm pretty foggy. So I've hit the deck at midday. Across the road, pretty much well from Keck HQ is a Starbucks. So I've staggered into Starbucks knowing no one in Hawaii for a coffee. And who should come in? Chuck Steidel. Got a coffee, come and sat with me. And I impressed upon him what it meant to me from my background there at the pointy end of optical astronomy on planet Earth. And he turned to me and he said, Trev, in his opinion, amateurs also had a contribution to make to astronomy. And what was I doing that night? My last night in Hawaii, and he invited me to put it in with him. So I got 3 nights on the Keck.
Oh, my God, Trevor.
So I took my hire car to the car park of Keck HQ, and I had to leave from there to catch my plane from Kona back to Oahu to get our connecting flight back to Australia the next morning. So heaps of things have happened to me to project me and along this path. It's just crazy.
That's an amazing experience. My goodness. Wow. I'm envious. It's wild. That's great. Well, I really want to thank you for coming on the podcast today. I really appreciate your time, and I wish you all the best.
No worries. Thanks very much, Tim.
All right. Okay, I just want to talk a minute about the ALPO has an annual conference every year, and it's going to happen in a few weeks. And part of that is an awards ceremony. And I've been lucky enough to be the chairman of the Walter Haas Observers Award for many years. The Walter Haas Observers Award is bestowed annually to the amateur astronomer for excellence in observational solar system astronomy. And this award is named for our founder and the original executive director, and it was established in 1985. The selection of this award is conducted by a committee convened by myself. Trevor, congratulations. You are the 2023 winner of the Walter H Haas Observers Award.
Tim, I'm overcome.
There you go. And it says
Tim?
Walter H Haas Observers Award, Trevor Barry, in recognition for your many years of interest in and contributions to observational planetary astronomy, especially Saturn. Julius had us put that in there, including visual and imaging, as well as professional amateur collaborations. The ALPO recognizes and values your expertise and commends you for your dedication to our organization.
Look, thanks so much, Tim. That's just an amazing honor. Tim. Thank you very much.
It's well-deserved. And the award consists of this plaque, and I know you're not currently a member of the ALPO, but you also got a complimentary 2-year membership to the ALPO.
Well, that'll be good.
So, and I just want to let you know the other committee members were myself, Richard Schmoody, Ken Pichetley, Randy Tatum, Julius Benton, Clyde Foster, and Matt Will. I've done this award for a number of years, and I have to tell you, for the last 5 years, your name has been in the top 3 every single year. And I was so thankful that you overwhelmingly were voted in this year. So congratulations, sir.
Look, that's just amazing. Absolutely amazing. God, who would have thought?
Well, it's well-deserved. That's all I know.
Yeah, no, look, it's not often I'm stumped for words, Tim.
Well, that's good. That's good. I'm glad, and we will get this in the mail to you. And hopefully, if you can attend the conference, it's going to be online. So I don't know if the time zones work, but I've recorded this, so we're going to be playing this at the evening of the banquet too, to show the presentation of the award. So again, congratulations, sir.
Thank you so much, Tim. Thank you so much.
All right. Well, again, it's been great chatting with you, Trevor.
Thanks, Tim.
All right. You have a good night or good day.
Good day, yeah.
All right. Well, that'll do it for this episode of the Observer's Notebook podcast. Again, I want to thank Trevor Barry for coming on, and as our guest today, and I hope you all enjoyed me presenting him with the Walter H Haas Observers Award for 2023. We upload new episodes of the Observer's Notebook on the 1st and 15th of every month. You can subscribe to us on iTunes. If you do, please rate and review us. I really appreciate it. You can also listen to us on Apple Radio, iHeartRadio, Soundcloud, Spreaker, Google Play, Stitcher, Amazon Echo, Spotify, and also this podcast is available on our YouTube channel. You can help support the podcast by donating to it via Patreon by giving up to $35 a month, where you will receive 1 year's membership to the ALPO and producer credits on the podcast. With that, I want to thank the producers of this podcast, Steve Siedentop and Michael Moyer, for their generous support of the Observer's Notebook. The link for Patreon, as well as the link for the ALPO, is in the show notes. If you'd like to get a hold of me, my email address is commentman@commentman.net, or on Twitter at ObserversNBpod. And until next time, my hope is you always have clear and steady skies. Thanks for listening.